Okay, this is chapter 2 on airflow and airspeed measurement. We're going to start with the properties of the atmosphere, which you'll see if you read in the books. Chapter 2 starts on page 17. It's 78% nitrogen, 21% oxygen, and 1% other. Why the atmosphere for pilots is that aerodynamics are going to be affected by static pressure, temperature, density, and viscosity. So viscosity refers to airflow. It's a little bit different than friction. Friction deals more with I guess you would say, a solid substance acting upon another solid substance, and viscosity deals with some type of liquid form, especially with dealing with aerodynamics. Here we're talking about air over the wing. You also see that in aerodynamics we try to use ratios, specifically the pressure ratio and the density ratio. These are also going to be in table 2.1. This is all based on standard static pressure, and standard, as you guys probably know by now, is 29.92. But the main reason we use ratios is because we cancel the units, and that's what you're going to see on page 18. All they're showing you there is how they derive the temperature and density ratios to get away from units. If we look at the ICOA standard atmosphere and we look at table 2.1, we'll look at a few things here. If we say we have a pressure ratio equal to 0.6877, then if you go to table 2.1 on page 20 and you find 0.6877 for the, let's see, pressure ratio, and you read to the left, you'll see that's a pressure altitude of 10,000 feet. Okay? Similarly, we looked at the density ratio. If we said we had one equal to 0.6292, and we read across there, you're going to get a pressure altitude of 15,000 feet. And density altitude is important because density altitude is going to affect our aircraft performance. So a lot of your aircraft charts are going to be provided for density altitudes. That's what's important because, as we said up front, aerodynamics are affected by pressure, temperature, density, and viscosity. So that's the atmosphere. That's how you use the table in 2.1, and that's what those density ratio and pressure ratios, temperature ratios mean. So let's move on and look at the continuity equation. This is pretty straightforward. This is for incompressible fluids only. So when we're talking about incompressible, we're mostly talking about airspeed and aerodynamics of less than Mach 1. That's a good rule of thumb. So if we draw a flow of air through a pipe, we call those station 1, station 2, and station 3. The continuity equation basically says the density at station 1, the area at station 1. Sorry about that. Sometimes the pointer here doesn't work very well. I'm really messing up now. Why it went red. So the density at station 1. Sorry, I'm not sure why my pointer stopped working. There we go. So density at station 1, the area at station 1, the velocity at station 1 is going to be equal to the same at station 2 and at station 3. So density here, area 1, velocity 1 here and here are going to be equal to for subsonic flow. Now, the continuity equation explains the relationship between velocity and cross-sectional area. It does not explain the differences in static pressure of the air passing through a pipe of various cross-sections. So Bernoulli deals with this, and this is how we're going to derive to get to how we measure airspeed. It is very, very important in aerodynamics and something that you guys should all certainly understand this concept. So let's draw a pipe again. Here's station 1, station 2, and station 3. You'll see that dynamic pressure, which we refer to as Q, is equal to 1/2 density times velocity squared, and this is going to be in pounds per square foot. You'll see that the book takes this and brings it down to Q equals density ratio times velocity and knot squared divided by 295. And all they're doing there is to use knots instead of using feet per second here in this velocity. This is a book geared towards pilots. So they try to do a lot of extra work, I think, in my opinion, of taking things to knots. So they continue deriving these things. But this is the equation for dynamic pressure. It's just that this is in feet per second in this equation. And if you look at equation 2.10 on page 22, that dynamic pressure equation is for knots. All right. So if we look at this, what we eventually get for Bernoulli's equation, which is total pressure H, is going to be equal to static pressure. So big P is always static. I always write P static, plus dynamic pressure Q. All right. And again, they're showing it here as density ratio, velocity and knot squared divided by 295. But this is the same thing as 1/2 rho v squared. Okay? So this is your equation for Bernoulli. Static pressure plus dynamic is going to equal total pressure. So let's visualize how over an airflow of a wing. If we draw this, we have velocity here of 100 knots, velocity here 200 knots, and velocity here at 100 knots. Pressure here is 2116. Pressure here is 2014. And the pressure here is 2116. So what Bernoulli is doing is quantifying the center cross-sectional piece. You can see at station 1 is equal to, if we call this station 1, station 2, station 3, station 1 is equal to station 3. However, what happens to the airflow over the wing, it's going to speed up and the pressure reduces. So over the top of the wing, velocity increases and pressure decreases, and this is how we generate lift in our airplanes. So this is an important concept to understand. It ties into airspeed measurement as well. So some of you are probably taking some other courses. I think it's aircraft systems. I can't remember, but I think they go through and explain how the airspeed pitot tube system and diaphragm works. So I'm not going to draw on the entire pitot tube system here. It is in figure 2.5 on page 24 if you want to take a look, but I'm going to try to walk through how we read airspeed. Okay? So first, let's just take, we say we took, there's airflow occurring. And in this airflow, we just put a piece of material. This square piece, I call it a 2x4. You're going to have on this 2x4, as air flows over it, some air is going to hit here, and most of the air is going to flow over the 2x4. Right here, air is not going to flow through. It's going to stop at this point and at this point. We call these stagnation points. Okay. So if we look at figure 2.5 and knowing that these are stagnation points, what we mean by stagnation points, at this point V is 0 and dynamic pressure is 0. But if you look at the pitot tube system, I'm just going to draw the first part. Airflow, and then into the diaphragm. So where we want to read this is we have a hole in the pitot tube system to record this air entering the system. And if we say outside at V1, so this is station 1 outside, okay, not station 2. So station 2 will be here, and station 3, okay, they don't have station 3 here. So station 1 here, station 2 is here. So this is our, if you remember the pipe, this is our Bernoulli part here. V1 is equal to 100 knots. I'm just taking this right from the book, guys. P1 is 2116. Dynamic pressure is 34. And total pressure is 2,150. So, therefore, we know that P2, which is here, is going to be equal to total pressure, right? Remember this, and this is the same, which is going to be equal to the pressure at 1, station 1, plus the dynamic pressure at station 1. And this is 2,150 pounds per square foot. So I have each here. Let's draw this again. So P2 is equal to total pressure, which is equal to the pressure at 1 plus dynamic pressure at 1, which is equal to 2,150. So the difference between the pressures, that's what we're after, is going to be H minus P1, which equals Q1. And this is what pushes on the diaphragm in figure 2.5 to give you calibrated airspeed. Indicated airspeed is what you read at the dial, and as you should know, at the dial it has some error, so a lot of times we are after calibrated airspeed. Figure 2.6 shows airspeeds for compressibility at high altitudes greater than 200 knots. And this is what we refer to as equivalent airspeed. And true airspeed is simple. It's equal to equivalent airspeed divided by the square root of the density ratio, not Q, it's the density ratio. And this density ratio can be found in table 2.1 in the book that we just had. So this is Bernoulli. Hopefully this made sense, but that differences in pressure in the pitot tube and the velocity speeding up at that stagnation point, and the differences between those two pressures is how we get airspeed. And that's important because, as you know, it's important to understand what happens when the pitot tube system becomes clogged and when the static pressure port becomes clogged, or they both become clogged. But to get airspeed, you need to have static pressure port and the airspeed. I'm sorry, the pitot pressure port. All right, so that's chapter 2. Thanks for listening, and let me know if you have any questions.